So in this video, what we're going to be talking about is how to analyze your results when you take a bunch of measurements and how to get the uncertainty on that, which is called the standard deviation. This material is found in chapter 4 of Taylor, the textbook that you'll be using, and I'll assign a few homework problems out of that textbook to go with this video. So the first thing we're going to talk about is, and really what we're doing here is the analysis of random uncertainties. And if your uncertainties are not random, so if you have systematic uncertainties in your system, all of this doesn't apply. This also only applies for something called normally distributed data, and so we'll talk more about that later. So the first thing we'll talk about, and so this is really what we're doing today. So the first thing we'll talk about is the best estimate of some value you measure. And so the best estimate, if you measure something over and over again, I think all of us have an intuition about how that works. And so the best estimate for that is actually the mean. So that is the mean, or the average. I'll call it the mean here. It's a little bit more sophisticated. So the mean is given by this equation here, x bar. So x bar means the mean. And what you do is you sum up over all the individual values, and then you divide by the total number that you took. And so that's the technical definition of the mean or the average. So if you measure some quantity a bunch of times, the best estimate of that value is the mean. That seems simple enough. So the second question becomes, what is the uncertainty on this? So the real question becomes, what is the uncertainty on that, or an individual measurement? So you might look at the average deviation from this. So if you take this measurement a bunch, you'd get some average value, and then you would find that you would have values on either side. So what we're going to call that is the deviation. So first look at the deviation from the average. So we can look at the average deviation. So we define the deviation. So we define the deviation as d, an individual deviation, which equals the individual measurement that you're taking minus the average value. So you would say, okay, you can find an individual deviation for each measurement. But there's an issue with using this to define the uncertainty, is that if you take a bunch of measurements, you should find that if you have a measurement on an average value, you'll have just as many measurements above and below that value. So if you measured the period of a pendulum and you said it was 1 second, you should expect to find individual values. Some of them are going to be higher than that. Some will be 1.2, 1.3 seconds, and some of them will be lower at 9.8, 9.6, that kind of thing. So if you take the average, so we'll divide by the total number, so this is kind of the average deviation value, you should find that the average deviation is 0. So that means the deviation isn't really a useful quantity to use to measure some kind of statistical uncertainty. But instead we're going to look at the d squared. So if you think about that, on average, if you give just as many above and below, it'll count 1.1, and 9.9 will basically be the same deviation from 1 if you do the square, or the square of their deviation will be the same. So what we're going to look at instead of average of d, you're going to look at the average of d squared. And so we call that the standard deviation, or sigma, and this is the full equation. I'll just write it right now. 1 divided by n times the sum over the individual values, subtracting off the average value, and then you square that. So you square it, and then you take the square root of it so that you go back to the same units you had before, the same dimensions. And so that's what's called the standard deviation. So this is standard deviation. I think many of us have heard about this before, and you might have even seen that equation before. But there it is. I'm not gonna. There's actually a correction to this, and I won't belabor this point. In reality, you have to replace this n with n minus 1. So in reality, the best estimate of this is the same thing with an n minus 1 in here. Everything else is exactly the same. I'm not really going to focus on why this is, but really this is the one that you should be using. This is the one you should be using. In reality, these things are so similar. They're rarely very different. So you can get away with using either one, but you probably want to end up using this one here in general. And so what the standard deviation is, and let's just kind of rewrite it is this is the uncertainty in a single, oh, gotta redo this. So I'm going to restate what this is. So if you think about the standard deviation, in words, what it is that this is the uncertainty of a single measurement. So this is an uncertainty in a single measurement. So if you measure the period of a pendulum 10 times, you can find the average of that, and you can find a standard deviation. The standard deviation will be, if you take another measurement of the period, the uncertainty on that measurement will be the standard deviation, or sigma. Now, before we move on to something else, I want to talk to you a little bit about how you calculate this. If you look at this equation, it's a little ugly due to the fact that you have the sigma value, so the large sigma there, the sum. And so if you had 100 data points, if you had to calculate the standard deviation, it would take a really long time by hand. So my one big thing to tell you is to never calculate this by hand. I will never ask you to do that. I don't think you should ever do it. Unless you're like in a statistics course where they're asking you to do that, then you have to. But nobody does this by hand. What you want to do is use a computer. Use a computer. Do this with a computer. Python can do it. Excel can do it. Sheets can do it. So if you're going to use Excel, what you would do is you would go into the cell and you would type equals STDEV, and then it's actually going to ask you, it's going to have two, P and S. S is the correct one up there. It's the sample standard deviation. And then you put your data in here. And that's how you do it in Excel or in Google Sheets. Never do this by hand. No one should ever ask you to do it by hand. It would take way too long. So that's my first word of advice. So now what we're going to do is talk about one other thing. Is that if you remember I said the standard deviation was the uncertainty in one measurement. So there's a different quantity we need for the uncertainty in the average. So that's something called standard deviation to the mean. This is also called, aka, standard error. or standard error of the mean. I've also heard it that way. The Taylor of the book we're using, we'll call it all three of these things. Usually standard error is what I'll call it, because it's used as an error. And so what that is sigma equals, and so this is like sigma x bar, if the other one was sigma x, equals sigma x divided by just the square root of the number of data points you took. And that's the standard deviation of the mean. And what this is the uncertainty in the average. So if you took the period of a pendulum 10 times and you found the standard deviation, if you wanted to know what's the uncertainty on an individual measurement if you did it again, that would be the standard deviation. But if you wanted to know how well do I know the average value, you would use the standard deviation of the mean. So what this is also useful for, this is useful for comparing averages. So if you were going to talk to another group across the hall, for example, and you both did the period of the same length of string, you would say, did we get the same result? Well, what you might do is take the average of the 10 trials you took, and then they would do the same thing, and then you would say yours is the value found plus or minus the standard deviation of the mean, or the standard error. So you would find the standard deviation, divide by the square root of n. If you look at this, the square root of the n is really interesting, because what that is doing is it says the more data points you take, the more certain you are of your value, which makes sense. If you do the same measurement over and over and over and over again, you should find that you're more confident in that value, the average value. So the standard deviation of the mean will decrease. Meanwhile, standard deviation actually will not increase if you increase the number of trials. You can keep taking data more and more, and the standard deviation should stay the same, because that's really the uncertainty on an individual measurement, not the uncertainty of the whole value that you found. So now becomes the question that you have some measurement, x, and you have some uncertainty on that measurement. All right, sigma x. So sigma, this is the uncertainty associated with x. And now the question becomes, how do you compare that to a known value? So this, if everything is normally distributed, I mentioned that earlier, and so this means all your data follows a Gaussian, and I may talk more about that later. If it doesn't, then we have a problem. But let's say it does. Most things do. Most things that we talk about are. So we have some sigma here, and this is the uncertainty. And you have x plus or minus some uncertainty. What this is really saying is that there's a 68% chance my value is an x plus or minus sigma x. So I didn't prove that to you. I'm just kind of telling you off the top here. And this has to do with what the normal distribution looks like. And we won't get in the weeds of that right now. So this is a 68% chance my true value, the true value, is found within this range. So that's actually not that high of a percent. 68% is high, but there's a greater than 30% chance that the true value, so you measured some value a bunch, but the true value is outside that range. So this is actually not a good threshold. There's a 95% chance the true value is x plus or minus 2 sigma. And that's kind of the threshold that we'll typically use in this course. If you've ever heard of p-values and a 5% difference, see, there's a 95% chance the true value is in there. There's a 5% chance that the true value that you measured is outside that range. And if you've ever heard of p-values and a p of 0.05, this comes from the same place. Now you might also say 95% is still not certain. No, you're not 100% certain. And in reality, you're actually never going to be 100% certain. So when you're doing this kind of science, doing statistics, it's all about probabilities. So you're never going to be 100% certain of almost anything. And if that weirds you out, I'm sorry. There are other fields of science where 95% is not good enough. So for example, particle physics doesn't use 2 sigma. I think it uses up to 5 sigma, which is wildly large. In my field where I worked in biophysics, 2 sigma was kind of the standard. It depends on what you're trying to do. So in this case, what you would want to know is the value measured within 2 sigma of a theoretical value? So let's do an example. You said you measured the gravitational acceleration as 9.6 plus or minus 0.2. And then I'll put the units on here. Meters per second squared. Okay. So this agrees with, it actually agrees with 2 sigma of the real value, which is 9.81 meters per second squared, because you would have to say 9.6 plus 2, so this value here is the sigma, 0.2, is going to be equal to 10 meters per second squared. So that means that those 2 values overlapped. If, on the other hand, you had 9.61 plus or minus 0.01 meters per second, let's say this is your result from your measurement. This does not agree within 2 sigma. So again, the 0.01 is the sigma, so you would have 9.61 plus, so I'm just doing plus because the value is lower than, 2 times 0.01, and I'm being lazy with my units, bad on me, and this is 9.65 meters per second squared. So this does not agree within 2 sigma of the real value. And so this is the kind of thing that you're going to do a lot in the lab reports, because you're going to measure quantity that you know ahead of time. Now, if you look at this value here specifically, there could be 2 things that are wrong. Well, wrong, but there's 2 things that could be off. One is that your value is just not close enough to the known value. So that would be something like a systematic error that caused you to constantly measure a G that's lower. The other thing is that the uncertainty could actually be off. So if you look at the uncertainty here, the uncertainty 0.01 is really, really small. So likely in this case, you've underestimated the uncertainty. So either you have a systematic error in the measurement, and that is the hardest thing to fix. You have to figure out what's wrong. Did I constantly under-time it? Did I measure too long or too short all the time? You have to kind of think about it, and it's really hard to pin down. There's a way to do that, and we'll talk about that next week. Or your uncertainty or your error is underestimated. And that is often the case, I find, in these labs, is that you underestimate your uncertainty. So when we're going back, and I'll zoom out a little bit here, whenever you're taking a measurement, what you're going to do is you're going to get a measurement. So here it's 9.6, and you have an uncertainty on that measure. And you're going to say, does it agree with the known value? So you're going to take the value, and then you're going to do plus or minus, depending. If it's lower than the actual value, you would just add it. If it's higher, then you just subtract it off. But here, it's 9.6 times 2 sigma. So this is really the measurement times 2 sigma. So this is, and we say the word sigma, and that's why, because we mean this is the sigma. And so that's how you use uncertainty in a measurement to compare to a value. Now, I've used the value sigma for both standard deviation and for general uncertainty. So when you do measure G experiment, it's actually not going to be a standard deviation. It's going to be an uncertainty from your fit. Either way, you can use the symbol sigma, and the discussion of it will be the same. Does it agree within 2 sigma? That's kind of the main thing. So the standard deviation is actually also really useful about talking about the future and predicting future events. So if you have some average value, x bar, that has some standard deviation sigma x, there is a 68% chance that a future measurement is in the range, is within, I'll say within, x bar plus or minus sigma x. So this, if you notice, is the same number as when I was talking about comparing a known value to an unknown value. It's all because we're talking about normally distributed data. So if you have an average and you have a standard deviation, you can actually predict what future measurements of the same thing might be like. So there's a 68% chance that any measurement you take in the future will be in that range. And you can probably guess that there is a 95% chance that a future measurement is within x plus or minus 2 sigma. So the standard deviation can really tell you the future in a way. It can tell you, it can make you help you predict what future measurements would be. Not to absolute certainty. Of course, there's nothing absolute in statistics, but it can tell you with a 95% probability that any new measurement will be this within the average plus or minus twice the standard deviation.